Sir Isaac Newton, what are you doing hanging out by that spring and that mass, and why is it going to the left? Yeah, it's a trap. Probably I'm filming the video sideways to make you pretend that it's a mass on a horizontal spring. So let's pretend that it is for a while, and I'm going to pull the spring to the left, and I'm going to cause then, well, I guess I've added some energy to the system, and you can see that the spring will rebound and bounce for a long time. This is simple harmonic motion, and it's awesome. Turns out that pretty much everything within some limit acts a little bit like a spring. I'd like you to take a moment and push your nose in. You notice that your nose pushes back a little bit harder the more you push in.
Ultimately, you're pushing it really hard, and your nose is pushing back really hard.
So that demonstrates that everything is kind of a spring. We can define some things for simple harmonic motion. Like, I'd like to define this leftmost point as A, when measured from the equilibrium location. So we've got A is the distance from there to there, and also the uppermost point compared to equilibrium is A as well, the amplitude. And then we can define things like period. Well, that's clearly the amount of time it takes to get from the bottom back to the bottom, and you could time that using some video analysis right now. And we could also define the maximum velocity and the maximum acceleration. We could look at the spring force. We could say negative kx and do all kinds of things. But I'm going to do that with a piece of paper. Hopefully you've gotten the idea of what simple harmonic motion looks like. And Newton is impressed. Let me just throw some knowledge at you kind of fast and furious style. We had a wall and a spring and a mass over here, and connected to the spring, and the mass was doing, well, let's put some bounds on the mass's motion. Maybe it was going to here, and it would crunch up to there, and this location here was equilibrium. At the center is equilibrium. So this distance here we can call the amplitude, and also this distance here we could call the amplitude. And we can define things, as I mentioned. We can define things like the period, and period is usually abbreviated with a capital T. So we'll put that down right there. And the frequency, well, frequency is interesting. It has units of hertz, but a hertz is the same thing as 1 per second. And so it's a rate, it's how often something is happening. And period, oh, what are units of period? Let's check that out. The units of period are seconds. So this implies a relationship. We can test it in a little bit, but this implies that frequency is 1 over period. If you guys are good with inverses, we could also note that period is 1 over frequency. This is the happiest little physics relationship that you'll ever see because it's really easy to get from one to the other. And a hertz is it's 1 per second, but it's also kind of like 1 cycle per second, or 1 revolution per second, or 1 rotation per second, you know, various things like this. That's what frequency means. And we're going to have something that's a little bit different than frequency pretty soon. So you got to be cool with straight up linear frequency. The next thing is to define position. And I'm going to define the position of this, I'm going to define the position to be starting from 0, the position of the mass, starting from 0, and let's say that it's positive this direction. This is going to be my x-axis right there. And then that would be negative x. So if we do that, we can make this definition. We define the motion. I think you would find it reasonable if I made the following graph. I'll make a graph of position as a function of time. And it should look like this. We're starting at a position of A, and as time goes on, the mass approaches 0 and goes negative to, ooh, what's that value? I guess it goes negative to negative A, right? And then it will come back to 0 and go up to A again, and then back down, etc. This is a graph of a function that you know and already love. I don't have to convince you of the beauty of this function. We got A here and negative A there. So I'm going to define our function as follows. It looks like x is equal to A times the cosine of, ooh, Ooh, this is interesting. It definitely depends on time, and it depends on time in a very interesting way. This, between here and here, that time is 1 period. But you know that the cosine requires arguments in radians. So I'm going to put in here, watch this, I think I'll do it in blue. It's going to be 2 pi divided by the period. Now this is an interesting statement. It means that when t is equal to capital T, the period, when the time equals 1 period, then the argument of the cosine, that's this business in here, the argument of the cosine when t equals t, let's write this out, why the heck not, right? When t is period, then it's the cosine of 2 times pi. Interesting. And the cosine of 2 pi is the same thing as the cosine of 0. And that means that the cosine of 0 is just 1, so that means that the position will be A again. Aha! So that's how they keep track of this. I'll go through this one more time. What if we waited for 2 periods? Check this out. When t equals 2 times the period, where do you expect the thing to be back again? Here's period, and 1 more period, it would get back. That's kind of the definition of period. That's what period actually means. Then we've got the cosine of, oh snap, if t, oh yeah, we're gonna have 2 times t here. T's will cancel out, and we'll have 4 times pi. The cosine of 4 pi is the same as the cosine of 2 pi, is the same as the cosine of 0. Cosine is this wonderfully repetitive function, so we could say, actually, the cosine of n times 2 pi, any number, where n is any integer, we could have n be any of this set of integers, but as long as we've got an integer number of 2 pi's, we're going to have that cosine equal to 1, which means the position, so we can say the position is A, every time a period finishes up. I hope that's all right with you. Now I want to make a new definition and say that, ooh, this thing, this 2 pi divided by period, that's omega. Remember that? Angular velocity. Now we're going to call it angular frequency. And they are pretty much the same thing. Angular frequency and angular velocity are pretty much the same thing. And it's got units still. Omega has units of radians per second. Or we could kind of call it revolutions per second. It's kind of like that, because, you know, remember, radians are kind of there, and sometimes they're kind of not there. It is what it is. Next step, draw this graph of, let's do it right here. I've got that graph of position, and I'm interested in velocity. And Kevin Killeen knows that if you take a graph and you want to find its derivative, you'll be looking at the slope. So here's velocity, and we know that velocity is defined to be the derivative of position with respect to time. So we'll look at this a little bit more detail. It's the derivative of A times the cosine of omega times t. Oh, right. Did you see how I could put that omega in there? Instead of 2 pi over t up here, see that? 2 pi over t, that's the same thing as omega. So I'm just going to write cosine of omega times t. It looks a lot slicker, I think. And omega is this constant. Omega is determined by certain characteristics of the mass and the spring. We'll see in just a moment. Maybe you kind of have an idea that it's determined by the spring constant and by the mass, but in an interesting way. So let's take the derivative of this function here. The derivative of the cosine, well, that's a lovely thing. The derivative of the cosine is negative sine. So we pull the a out, and I'm just going to say a times, we'll do this in 2 steps, a times negative sine of omega times t, and the chain rule says we have to also multiply by the derivative of the argument of the cosine, and that would just be, just the derivative of omega times t, that's just going to be omega. So we'll clean this up a tiny bit. It says negative a omega times sine of omega times t, and I'm going to try to draw that right now. First of all, if I'm drawing the velocity, I notice that its bounds are going to be a omega. I don't know whether omega is less than 1 or more than 1, so I'm just going to draw its bounds here as a omega, and here's the other bound as a omega. That has to be negative down there. And I also notice that it's a sine function and not a cosine, so now I'm talking about starting down at 0, and it's negative, so it's going to be going negative initially, but it has exactly the same period. So if I take this dotted line, I need to be able to go to here and find that I'm going down again when I get to there. So this is a little bit tricky. Let's identify some more key locations. Let's identify the, what color do I want to use here? Let's identify the slope here on the position graph is 0. So I know I need to be at 0 right here. And the slope is 0 here, and the slope is 0 here. So my velocity is 0 at those points. My velocity is very negative right here. Very negative right here. And it's very positive right here. There. All right, good. And it looks like it's very negative again right there. Let's draw this sucker. We're starting at 0. We're going negative. We're going positive. And we're going negative. Again, like that. And this is a period. Period is the amount of time between there and there. And the graph is so similar, and because you know how to do calculus, it's a lovely thing. I want to point out before we go on that V max is equal to A. We don't have to pay attention to the minus sign. The maximum velocity that we ever get is A times omega. The maximum position that we ever got was the, it was the amplitude. X max is equal to A. You want to make a guess what the maximum acceleration is going to be? I'll let you consider that for a moment. And I'm going to take this and move it up and do a derivative again. Ooh, dang. Let's go back to the teal background. Check this out. I want to think about acceleration, and I know that acceleration is the derivative of velocity with respect to time. So this is d dt of negative a omega times the sine of omega times t. So by the same procedure as before, we notice we can pull out the negative a omega. They're just constants. And then inside of here, I need to do the derivative of the sine function. Derivative of sine is cosine of omega times t. And then I have to multiply by the chain rule. I have to multiply by the derivative of the argument of the cosine function. Sorry, the derivative of the argument of our sine function previously is again just an omega. So check this out. We get negative a omega square times the, let's see, where am I? The cosine of omega t. All right, cool. That's not a parentheses. It's the beginning of my cosine. There we go. Sorry. Now, I notice that is the bounds on our new function, and of course our new function is acceleration versus time. Look at this, I didn't even label my axis over here. This was velocity versus time. So I'm going to put some dotted lines down here, and I'm going to trace this sucker down. Let's see, when the velocity is level, that means there's no acceleration. So I expect no acceleration here, and I expect no acceleration here, and I expect no acceleration again here. And I expect maximum acceleration when the velocity is changing really dramatically. That's going to be, ooh, let's put those bounds on here. Here are those bounds. This is a omega square, and this is negative a omega square. And the bound is peaked right here, dot, 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 dot. And we've got a trough right here. Ooh, this is the negative cosine. So of course it starts at -1, and we're gonna have, starting at -1, it's a times omega squared times -1. We'll start down there. And then we have a negative velocity change down here also. We're gonna be there, and I need to connect these dots. Get ready. Here we go. It looks like this. Oh, it's a negative cosine. Okay, awesome. And we can go back up to here and say, yep, we know what our maximum acceleration is. It is a times omega squared. And we can make some really, really awesome statements here. The next statement that I want to make is that force is negative kx. It's a mass on a spring, for crying out loud, right? Watch this. That means, let's say that it's the total force on the system. That means that mass times acceleration is negative k times x. Are you ready for this? This is really awesome. Follow through each step. Make sure it's good for you. I'm going to plug in the acceleration equation. This is mass times, oh boy, negative a times omega squared times the cosine of omega times t. I plugged that in for the acceleration. Now my left side says it's negative k times x. Now x, oh shoot, x was just a times cosine of omega times t. And now we see the cosine appears twice. This equation doesn't depend on time anymore. I'm going to say that one more time. The cosine of omega t appears on each side of the equation, so it can be canceled out. What else can be canceled out? Look for it, look for it. Yep, the amplitude also doesn't matter. And you can do yourself a little bit of algebra and conclude that omega squared is equal to negative k. Oh, dang. Wait a second. Negative k divided by negative m, which is just k over m. So omega is the square root of k over m. If we were to put all this together and make one awesome equation, do you understand the significance of what we've just done? We found the angular frequency of a mass on a spring. It's that. Let's put a wow there, and maybe a flower pot. I think this deserves a flower pot. The flower in it? Sure. We can do a flower, all right. And what I'm going to do is I'm going to conclude that this is the full equation for the position of a mass on a spring. The position depends on time, and it's like this. This is how the position of a mass on a spring depends on time. It is the amplitude times the cosine of, now instead of writing omega times t, I'm going to write what omega actually is, k over m, screwed times time. Wow. Here's another wow. Cool, we'll put another one down here. Wow. For simple harmonic motion. Like, I'd like to define this leftmost point as A when measured from the equilibrium location. So we've got A is the distance from there to there, and also the uppermost point compared to equilibrium is A as well, the amplitude. And then we can define things like period. Well, that's clearly the amount of time it takes to get from the bottom back to the bottom. And you bring and a mass over here and connected to the spring, and the mass was doing, well, let's put some bounds on the mass's motion. Maybe it was going to here and it would crunch up to there, and this location here was equilibrium. At the center is equal that the spring will rebound and bounce for a long time. This is simple harmonic motion, and it's awesome. Turns out that pretty much everything within some limit acts a little bit like a spring. I'd like you to take a moment and push your nose in. You notice that your nose pushes back a little bit harder the more you push in.
Ultimately, you're pushing it really hard, and your nose is pushing back really hard.
So that demonstrates that everything is kind of a spring. We can define some things, if you could time that using some video analysis right now. And we could also define the maximum velocity and the maximum acceleration. We could look at the spring force. We could say negative kx and do all kinds of things. But I'm going to do that with a piece of paper. Hopefully you've gotten the idea of what simple harmonic motion looks like. And Newton is impressed. Let me just throw some knowledge at you kind of fast and furious style. We had a wall and a spring. Sir Isaac Newton, what are you doing hanging out by that spring and that mass? And why is it going to the left? Yeah, it's a trap. Probably I'm filming the video sideways to make you pretend that it's a mass on a horizontal spring. So let's pretend that it is for a while, and I'm going to pull the spring to the left, and I'm going to cause then, well, I guess I've added some energy to the system, and you can see